This is the project that Co and Calvin and myself, Kevin, worked on. So we've got right here, we've got a few abstractions here. Right here, this is the 6-band filter. This is Calvin's work. It's where all the audio gets filtered into 6 different bands. And then those 6 different signals go into the tempo magnitude finder, which has a poly object for each one of these signals, and then you can designate how many voices you want per poly object. That will affect this tempo bank right here, which contains hertz values that correspond to tempos. So we have the minimum tempo right now being 40, which corresponds to 0.68 hertz. And it's a length of 25, which is 25 voices. So if we change that, then we should see also a shift in this. So now we have 28. This is Co's work, the BPM out peak picking. What this does is it uses these accumulated values from the tempo magnitude finder, and it uses it to output a peak. It outputs a peak index, which then corresponds to this bank here, and then we can use these hertz to calculate a detected tempo. So I can, let's open these up. I can go through them individually here. So like I said, this is Co's work right here. What this does is it has 6 different jitter matrices, these BPM filter matrices, and this receives these receive all of their values from the tempo magnitude finder, and all those poly voices and objects. So those are all summed up into this BPM filter matrix, and then it's iterated through to find the peak or the max value, and then we take the index of that max value, and I added this to be able to integrate it in with the tempo magnitude finder. So we get the index of the max here, and then we use that to find the hertz value and then calculate that to BPM. This is the tempo magnitude finder. You can see here, these are the 6 different poly objects. Each of them, it says 100 voices here, but on load, it starts up with 25 voices per poly object. So each one of the individual frequency band signals comes through here and goes into this tempo track 2 poly object. This is tempo track 2 poly object. So what this does is it receives that source signal on its respective frequency band, and it's multiplied with the cosine and sine wave at a corresponding hertz from the hertz tempo bank. And you see if if we've got 28 voices and this was voice 1, then this cycle and or this cosine and this sine wave would both be at 0.683 hertz. Their values are accumulated and then reset every period of this tempo, this hertz tempo. And then we use this nice function. Co and I worked on this, figured this out to be able to just send the very last sample of this accumulation before it resets. Then it's converted and goes through the smoothing function, and then is poked into those BPM filter matrices in Co's peak finder. So this is Calvin's 6-band filter, and I've added this just for the abstraction so that we can visually monitor the audio is coming through. He built this PFFT object, which gives us a low and high pass on the ends here, and then we have 4 bands within these frequency ranges. So the signal is being separated into these 6 different bands. So for the purpose of testing this patch, I'm using the clap audio clip, and it is being triggered according to this set tempo here. So we can see our range right now is 40 to 68, so let's do a tempo range, or within the tempo range. So let's pick 54. These coefficients right here are for the ramp smooth function in every single poly voice. We'll just leave those there. Got 28, 40. Okay, we'll turn this on. That'll start. as an artifact of the tempo magnitude finders method, each of those poly voices, we get this strange waving behavior in the data. So what has to happen is, in order to find what the actual peak is, because the peak might be here but not necessarily present always. So you'll see that these values kind of go up and up and up in a strange waving format. And so what I do is I take several subsequent, I guess, concurrent peaks over the course of 10 seconds and then find the peak of those peaks. That usually gives a fairly accurate value. This is a really finicky patch. It'll be really accurate sometimes and not accurate in others. I find that whenever I mess with these voice amounts, the number of voices per poly, things tend to become less accurate. There's some strange, I don't know, something strange that happens with the poly object. Things don't quite load in correctly, and the patch seems to deteriorate in quality the longer I have it open. And sometimes by resetting the DAC, that helps maintain accuracy. But I'll close it and open it up again and see if, just by using all the defaults, see if we can get a more accurate tempo reading. Okay, so I've reopened the main patch here, and all we've done is change tempo so that it's within this range, 40 to 65. Let's choose 51. Let's see, it had 51 before, so sometimes this will maintain an accurate offset. So its error might be -3, you see it's -4 here, and then if I increase it, it might maintain that same negative offset, and so it'll maintain some kind of precision. But I find that this is really, really finicky. Sometimes I'll open it up, it'll be very, very accurate. But then there are other times where it'll be much less accurate, a little bit like right now. It seems to be a lot less stable. And even though there's, let's see, with the CPU monitor I've got right here, doesn't show it overloading or anything, but I find that if I have other processes going on my computer, like right now with video capture and audio, something strange happens with these jitter matrices. They don't completely finish all of their calculations before the next calculation begins. Because we have so many voices and so many things going on, it's just so very computationally expensive. So I think maybe a future iteration of this might involve maybe, I guess, avoiding the use of a jitter matrix, trying to figure out some other way to accumulate all these values, and then also to take into account the need, I guess, for windowing with this tempo magnitude finder, because all the polys are acting independently. They're all taking they're all calculating based on their own hertz value and their own period, instead of having a synchronized window. And I think that might be essentially what's producing the strange waving function in the data.